Section 1, Polygons, Video 3. Here we have 3 more examples just to illustrate how knowing linear pairs or corresponding angles or interior angle measures is so powerful in being able to find other angle measures. So for example number 4, we need to find the measures of those 4 angles. Well, I see initially that I have this 110 degrees right here. I really like corresponding angles, so since these 2 lines are parallel, you see right here, I know that this is a corresponding angle, and I know corresponding angles are equal, so I see that right away y equals 110 too. Oops, 110, because it's corresponding with this 110 degree angle. And I see a linear pair. Since that's 110 and this is a line, I know that this measure must be 70. So I know that W equals 70 degrees. I also know that X is a corresponding to that 70, so those must be equal. So X must also be 70. And Z is the only one I've left. And there's a couple ways I could do this one. I see that these are parallel lines and that this is a right angle. And so those are same side interior. So they must add up to 180. And since the other one is 90, Z must also be 90. I could also say that, well, we have a quadrilateral here and the angle measures must add up to 360. So if I do 360 minus 70 minus 110 minus 90, so I was just subtracting these other angle measures, which I know this one is 110 and I know this one is 90. So I just subtracted to find that missing one. I also know, since they're parallel lines and this is a right angle, the other one must be a right angle as well. So there's a few ways to prove that one. But there we found all our missing angle measures. Example number 5, given a regular heptagon, so it has 7 sides, what is the measure of one interior angle? Well, I initially saw regular, so they're all the same. So all I have to do is find the sum of them and then divide by how many there are. So since there's 7 sides, I do 7 minus 2 divided by 7 angles, or 7 sides. And if you put that in your calculator, you have 180 times 5, and then divide that all by 7, and you'll see it's 128.6. So that's the measure of one of these angles, which looks about right, because it's less than 180, but it's more than 90. So I believe that. The last example, if a figure has an interior angle measure of 135, can it be regular? Now for number 5, it was okay that we had a decimal in there. That's totally fine for an angle. But for this one, we're solving for how many sides does it have? And we can't have a decimal for that. So we know if we get a whole number, it must be regular, and it works out. So for this one, we can set up our equation. We just have some different givens and unknowns. So we know one of the measures is 135, but if we set up the equation to find that, so we don't know how many sides there are, we would have this. So n sides, we're saying the sum is 180 times n minus 2, and then if we divide by the number of sides, we should be able to get that one interior angle measure. So let's see if this works out. If we solve for n, if we get a whole number, it must work out. So for this, I would multiply both sides times n to cancel out on the left side. Then I would distribute to have 180n minus 360, because that's 180 times 2, still equals 135. I'd add 360 to both sides to get rid of it on the left, which would leave me with 495. And then if I divide 495 divided by 180, I'm going to get n equals 8. So, therefore, I'm able to conclude that we have a regular octagon. because it worked out to give me a whole number. So if a figure has an interior angle measure of 135, it could possibly be a regular polygon. We don't know that for sure, but it could be a regular octagon.